Hello, my name is Ted Herman, and I'm a high school physics teacher. I also teach astronomy, and I've been teaching in some capacity for about 30 years. I'm always very interested in space. One thing in the physics class that we dabble in is universal law of gravity. We usually mix it with circular motion, and if we run through that process, we can calculate the speed of the Earth. Somewhere around 30 kilometers per second, a very fast object compared to the speeds that we're used to walking around on this fine planet. But one thing that we fall short with in that is that you can do the calculations, but then you can't verify it with experiment, uh, or so I thought until recently. So uh, most things that move are very easily detected with a radar gun. A police officer is going to use the Doppler effect to measure the speed of vehicles moving around. Radio astronomers or any astronomers are looking at it, the light coming in from the universe and trying to figure out what's going on. If they're looking at a galactic rotation, kind of in that one picture at the top there, uh, then they want to get a sense of what the galaxy's doing as a whole. And for them, the Earth's little piddly motion around the sun can be a bit of an annoyance. They want to subtract it out. They want to know what the galaxy is doing around its center. And if we're moving and using our radar guns, a police officer doesn't drive around pointing his radar gun, he sits still. So, uh, just going to move on here. I want to spend a little time giving thanks to coming across the opportunity to find an instrument that will be able to allow us to measure the speed of the Earth and verify it. So I came across a number of years ago at the National Science Foundation back in 2017. I think I was aware of it. I wasn't able to make it that summer, but digital signal processing and radio astronomy, combination of some electronics engineering and some astronomy in there. And we spent 4 weeks at West Virginia University and 2 weeks at Green Bank National Observatory, where they do a lot of radio astronomy up there. Uh, so there's a lot of things that we can do. We built this simple little telescope. Well, it's not simple, but it's easy to make. It's definitely brings it within reach of the high school classroom. If you look at the picture on the right, you see this thing. It might stand about 4 to 5 feet tall at its highest point there. That is foam insulation. The radio waves are reflecting off the metal and channeled down into a little paint thinner bucket. A simple lumber stand and a nice low noise amplifier attached to the bucket and a software designed radio uh, piece of hardware, the Air Spy in this case, commercially made. That brings it all into the computer, which I'm going to get myself out of the way so that we can see that. Uh, so there's you're detecting neutral hydrogen in our Milky Way, and it does a pretty good job of doing that. You can get some nice strong signals from it. You can figure out what the main frequency is of the objects you're looking at, and science can be done. We all had to kind of take on a project, and I ended up taking on a project using it to measure the speed of the Earth as one of the things that I did. So, uh, just kind of a quick little review of that high school physics. We have the universal law of gravity, circular motion, and at New York State, Doppler effect is no more than recognizing that if an object is coming at you, the wavelengths will get shorter, the frequency will get higher, and that's a blue shift. And vice versa for if they're going away, wavelengths are longer, frequencies are lower, and you have a red shift. The math for low speed objects, which the Earth would be at 30 uh, kilometers per second compared to 300,000 kilometers per second, that's a slow object. It's 1/10,000th the speed of light. And the question is, can we detect that? And the answer is going to be yes. So in this case, in the picture there, I have a little cartoon police officer at the center of the galaxy looking and checking out the Earth going around the sun. But if we went vice versa and he was riding on the Earth and pointing at the center of the galaxy, sometimes the center of the galaxy would appear to be going away from us and then coming towards us. So we would expect red shifts and blue shifts in that. So there's a few things that we have to do in this, and we have our one situation. We have a planet going around the sun that we live on. It forms the ecliptic plane. It's fairly circular. Yes, we do know it's elliptical, but it's near circular. And for this experiment, we're going to um, play with that idea. It is convenient that the plane of our solar system is kind of lined up close to the center of the galaxy. I chose the center of the galaxy. It's a very strong radio signature there, so it was a nice, easy target to aim at and get a signal from. Uh, but we have to remember that the Doppler effect is a radial motion, so things have to be coming towards us or away from us. In the little picture here, if we were in a helicopter looking down on some object going in a circular motion, we would not be able to use the Doppler effect. It's never getting closer to or further away. So very conveniently, we're almost exactly on that galactic plane, just by coincidence. I assume that the orbit was circular. I think officially it's closer to 29.8 kilometers per second. So that was something that I did. And I made observations of the center of the galaxy when it was crossing the meridian in the sky. So one fun thing about that is I did a long year experiment and watched for a full circular path, which means that I had to go out essentially 4 minutes earlier every day. And over the course of the year, I got to experience all times of the day in getting that done. So um, it all kind of started in my first year. I was looking at the center of the galaxy for whatever project I was working on at the time. And in my mind, if the Earth was going around with the sun around the galaxy in a nice circular motion, and I'm looking at the center, nothing on average should be getting towards or away from us. So when I saw this very symmetrical thing, yes, there's some gas. There's going to be clumps of gas that are coming at us and away from us. And the resolution of the Horn telescope is about 20 degrees. So you're looking at a pretty wide piece of sky. But the fact that the peak is fairly symmetrical is what I would expect. But I was bothered by the fact that it was off that center line. The center line's at 1420.4 megahertz, which is the neutral hydrogen frequency. So it seemed to be a little bit lower frequency, slightly redshifted in that case. And I was wondering what might have been the cause of that. So I kind of posed the question to some astronomers there. I said, "Will we be able to detect the Earth's motion in that, in the Earth going around the sun?" And most of them said no. So I was still curious enough to kind of follow through and did some preliminary math, and things are fine. So what I'm going to run through here is a sequence of about every month. This was July. Oh, this was the first one I took, and then the next summer when I went back, I took another image. So I'm going to shift to another spectrum of a year later. I think it might have been a day early, but basically, if we watch that again, it's pretty much in the same place. And the shape changes a little bit. It's the instrument, it's the pointing. Uh, but now I'm just going to kind of walk a month ahead. So that was July. Here's August, and here's September. This is very close to when we are heading directly away from the center of the galaxy. So, if you're watching a race car, this is when it's going around the far turn. It's going to start to go on the back straight. That's kind of the way we can imagine that. So we see it coming back, and there's November and December and January. December is when we're on the back stretch. So we're coming around, and then we're going to start to head back towards the center of the galaxy. March is about another 3 months. We're kind of heading at it, and then we're going back. There's June. I had to steal a June from the previous year, but they lined up nicely. And no, I thought I put a July in there. All right, maybe I didn't. There we go. So, what did I get at the end of it? I had all these data points, somewhere around 50 data points in a little over a year. Uh, and the line there is just it's just a sine wave. I picked December 18th as my start point of the sine wave because that's when we're pretty much opposite the center of the galaxy. So we're kind of at the far part of the outside of the turn going back in, and I just made a sine wave with 20. You can see that it's just below 30, 29.8 uh, kilometers per second. And my data points are on there, and they're kind of riding a nice sine wave. So, there's some question that might be forming in your mind with the sine wave right now. I put the blue dots in there for when I got into the second year, so I saw the data overlapping nicely. Um, the data points are above the expected value, though, so that was kind of interesting. They all seem to be kind of riding high. Um, the positive numbers are representing blue shift. So a little deeper research kind of found out that the Earth is not in a circular orbit around the center of the galaxy. It has its own elliptical orbit, and it has a radial component, which is towards the center. Astronomers are still wrestling with what that number is and doing the research. I found ranges from about 6 to about 14 kilometers per second towards the center of the galaxy with an average around 10. So I was it was a nice bonus in this activity. Yes, I did verify a kind of sinusoidal component of the velocity as we went around the sun, but I also kind of eked out of it the ability to kind of confirm the radial component of the sun going uh, around the galaxy, center of the galaxy. So this is very exciting. It's been a very neat experience for me to have this opportunity and come across an instrument that could help me verify the speed of the Earth around the sun. Thank you very much.